Okay, so back to testing polar equations for symmetry. And there's three different types of symmetry that we'll be looking for. And the nice thing about looking for symmetry, if you find it, is that you can just draw half of the graph and then know what the other half looks like because of the symmetry that you have found. So you may have done this before with algebraic equations, so it might seem kind of familiar. So we're going to start with symmetry with respect to the polar axis. So this would be the x-axis if we were in rectangular coordinates. So think about, we're talking about symmetry with respect to the polar axis. So we're asking if you see symmetry along a line with the same theta and negative theta. So if this angle is theta and this angle is negative theta, that's what you do to test for the symmetry. You replace the thetas, any thetas in the equation, with negative theta, remembering that because sine is an odd function, we get sine of negative theta is negative sine theta, and cosine is an even function, so if you have the cosine of negative theta, that's just cosine theta. So if you get back your original equation after doing that replacement and a little manipulation, then that tells you you have symmetry with respect to the polar axis. So that would be this type of circle, would have symmetry with respect to the polar axis. You can fold it about the polar axis and it matches up. So then the next thing will be symmetry with respect to the line theta equals pi over 2. So let's see, theta equals pi over 2 means the angle keeps being pi over 2 and r goes through all its different values. Oh, so this would be the y-axis in rectangular. So we replace theta. So if this was your theta, you replace theta with this angle, which is pi minus theta, and see if you have this type of symmetry. And that would mean that your picture looks something like this, where you're symmetric about that line. And then the last one is symmetry with respect to the pole, which would be the origin in rectangular coordinates. And this one's pretty easy to see. If you replace r with negative r, and then you get your equation back, so it pretty much is going to have an r squared, or an r to an even power for that to happen. So this is an important note and kind of subtle, but we're to the point of learning about subtle things now. So here's the note. If you pass one of these tests, it guarantees that you have symmetry. So yes means symmetry. Unfortunately, failing the test doesn't necessarily mean there is not that kind of symmetry, just that the test didn't find it. So yes means symmetry, no means I don't know. And you're going to run into other things in math that work this way. So just start getting used to it now. So if you pass the test, guarantees symmetry. If you don't pass the test, you don't know. You have to do more work. You just have to do the whole graph. So we'll be using these tests when we're graphing polar equations to help speed up our work. So this is a little table that's right out of your book that shows a lot of the graphs that you get by graphing different polar equations. So we're going to graph polar equations by plotting points, and we're going to check for symmetry. So r equals 1 plus sine theta. The first symmetry test says replace theta with negative theta. Okay, so we're going to go r equals 1 plus the sine of negative theta, which is 1 minus sine theta when we use the fact that sine is an odd function. And you say, nope, this doesn't appear to have symmetry about the polar axis. So now let's try looking for symmetry about the vertical axis. So replace theta with pi minus theta. Okay, so we'll have r equals 1 plus sine of pi minus theta. And here's a handy dandy place to use your identity that says, oh, that's sine pi cosine theta minus cosine pi sine theta. Sine, cosine, cosine, sine. pi, theta, and a minus makes a minus. Okay, so the sine of pi is 0. The cosine of pi is -1. So -1 is plus, you get 1 plus sine theta. So we do have symmetry about the line theta equals pi over 2, or the vertical line. So that means if we draw the right side of the graph, the left side looks identical. And we can tell pretty obviously that we don't have the third type of symmetry, because if you put -r in there, it's not the same. So those are the 3 tests for symmetry. So now let's plot a few points and see if we can tell what this looks like. So if theta is 0, sine of 0 is 0, and r is 1. So I'm going to use a bigger scale here so you can see. So I'm going to use 2 circles as 1 unit. So this is 2, 3, 4, etc. So here's the first point. Theta is 0, r is 1. Okay, then we have a sine, so let's use pi over 6. So when theta is pi over 6, we get r equals 1 plus sine of theta is a half, so 3 halves. This is another reason to make the scale bigger, because it's easier to graph halves. So when the angle is pi over 6, I go 1.5 away from the pole. Okay, and then when I have pi over 2, the sine is 1, so r is going to be 2. So I have 1, 2. And then 5 pi over 6 is going to be another easy to calculate point. So 5 pi over 6, the sine is still a half. So we'll get 3 halves when theta is 5 pi over 6, so 1.5. And then when I get to pi, the sine is 0 and r is 1. Okay, so let's keep going. If I have 7 pi over 6, now the sine of theta is -1/2, so r is a half. So I'm at 7 pi over 6, r is a half. And then when I'm at 3 pi over 2, sine theta is -1, so r is 0. So that's where the pole is, a point on the graph. And then let's do one more of 11 pi over 6, where the sine's going to be -1/2 again, and so r is going to be a half. So this is a shape called a cardioid, and if I'd made it even bigger, that would have been even better. So that's a cardioid. And if you look up here in the table, you can see it was r is 1 plus sine theta. So the a and b were the same number, and it was with sine theta. So that's what made it be upward. Okay, so we'll do this next one in class together, and this last one, and then do expect a problem similar to the problems on this page in your text on the test, but not the one next Friday, the one after.